Okay, so we discussed about the switching function, and we use the switching function to compute the output voltage and also the input current. And now we want to use switching function to calculate the voltage across the switch. So the switch voltage. So what is switch voltage? This is S11 switch. So here we have plus, minus, plus, minus, plus, minus. So if you have a loop go here, what is the voltage across the switch? Then it should be plus here, minus here, and then go here, right? Because it is series. So if you have V1, then you have switch, and then you have output here. So what is the switch voltage? It should be V1 minus V out, right? So we have plus here, so this is plus, and then minus, go to the low. So now my question is, what is the switch across H11? So what is the voltage across S11? So we can write down, it is V S11, S11. So this switch. So what is the voltage across S11? It is equal to this voltage minus this voltage, right? So what is this voltage? V1, right? So it is V1, this is input, minus this voltage, right? Output, V1, this is output. This one means J equal to 1. This one means I equal to 1. I is input, J is output. So this means this voltage minus this voltage. So how our input voltage always constant? So it is V1, no problem. But how about output voltage? Output voltage is here. So if you want to say J equal to 1, what is output voltage? It is H11 V1 plus H21 V2 plus H31 V3. So you can write down, it is equal to H11 V1 plus H21 V2 plus H31 V3. So this is Vj, and J equal to 1. This is output voltage, right? So you can check here. J equal to 1, H11 V1 plus H21 V2 plus H31 V3, right? So you can write down this one. And then you also can write down a simple way. This is Vi minus Vj. So Vj equal to summation Hkj Vk. So K from 1 to 3. So it is like this. So we can calculate the voltage across the switch S11. So S11 switch voltage, right? So why do we need to calculate S11 voltage, switch voltage? Because we need to know how can we define the voltage trace. How many voltage should be the switch in dual, right? If the voltage trace is higher, then the device become more expensive, right? So we need to know what is your voltage trace then you can design this voltage. So this is voltage stress, voltage stress. So how about the current? So S11 switch. Current. What is the current? So if this turn on, then we can have a current go this way. Go this way, right? So how many current flow through the switch? So we can say this is IS11, ISIJ. So it is current through the switch. So how many current? So it depends on this current. So we call this is IJ. J equal to 1. So this is IJ. Could be 10 ampere. So this is 10 ampere. However, the 10 ampere comes from 3 ways. This switch turn on, this switch turn on, and then this switch turn on, right? Total is 10 ampere. For each switch, maybe only 3.3 ampere, right? Because you have 3 switches to share 10 ampere. So how can you describe this behavior? Then you have to multiply by duty cycle, Hij. So Hij could be only 1/3. So like this, 1/3 for the full duty. So what is your current rated? This is 10 ampere, but the duty is 1/3. So how about the average? 3.3 ampere. So we can break down in this way. So this is the current flow, the switch. So we can calculate the current through the switch. So now we want to express in more convenient way, because this equation is not easy to understand. So how can I write down another way? I want to know output voltage. What is the output voltage? Output voltage, we have J equal to 1 to 2 to 3. So we have V1, V2, V3. So this is J equal to 1. This is J equal to 2. This is J equal to 3. So it is related to input voltage. So this is I equal to 1, I equal to 2, I equal to 3. So how about this voltage? This voltage is this voltage multiplied by this duty plus this voltage multiplied by this duty plus this voltage multiplied by this duty is equal to this voltage, right? So how can you describe this behavior? So it is H11, then H21, H31, right? So output V1 equal to H11, V1 plus H21, V2 plus H31, V3. So this voltage equal to this voltage multiplied by this switch, this voltage multiplied by this switch plus this voltage multiplied by this switch, right? We learned it before. Then how about this one? So we can write down J equal to 2. So H12, H22, H32. So if we want to learn this voltage, it is equal V1 multiplied by H12, V2 multiplied by H22, V3 multiplied by H32. It is this voltage. How about this voltage? We have H13, H23, H33. So this is input voltage vector. This is output voltage vector. This is switching function matrix. So we can easily develop this relationship. So it is easier. So we can easily compute the output voltage. We just use matrix. So if we can do this, then what can we do? We can call this is matrix 3 by 3. 3 by 3 matrix. We call H 3 by 3, right? Only a matrix. How about this one? This is a vector. So we have V1, V2, V3. So this is 3 by 1. So 3 by 3 multiplied by 3 by 1 become what? 3 by 1, right? So you learn matrix. B equal to HA. This is 3 by 1. This is 3 by 3. How about this one? 3 by 1. So it is correct. It is correct. So we can easily get this one. No problem. So we can write down this one. No problem. Okay. So this is V out and V in relationship. V out and V in relationship. So we can obtain this relationship. Okay. So we learn everything. Then I ask you another question. What is the harmonics here? What is the harmonics here? What is the harmonics here? What is the current harmonics here? What is the current harmonics here? What is current harmonics here? You say, I don't know, right? It is too complicated. So now we want to analyze the output harmonics and the input harmonics. So we should learn it from switching function. But the switching function is like this. Do we take this is time domain or frequency domain? It is time domain. If it is time domain, can you learn its harmonics? I give you a time domain. I ask you, what is the third harmonics? What is the fifth harmonics? You say, I don't know. If you want to know the harmonics, how can you do? You have to convert to what domain? Frequency domain, right? So you have to convert time domain to frequency domain. Because in frequency domain, you have Fourier series. Then you can learn 60 Hertz, 130 Hertz, 300 Hertz, how many components. So this is frequency domain. So what we learn is time domain switching function. But this is not enough because we want to learn what is the harmonics here, what is the harmonics here, what is the harmonics here, what is the current harmonics here, what is current harmonics here, and what is current harmonics here. Can we change the switching function to reduce the current harmonics? So we need to learn the frequency domain. So how can we learn the frequency domain from the switching function? If you have a switching function, how do you know its frequency domain? So then we have to use Fourier series. So we have waveform like this. So we know this is 1. This is 0. Right? We learned that. And we know this is 1/3. So this is 1 period. But 1/3 here. So because we have 3 switch, so we occupy 1/3. And this is B phase, this is C phase, A phase, B phase, C phase, right? And the opportunity is 1/3. 1/3. So now I ask you, what is the frequency? What is the Fourier series? If you have a waveform right here, then if you want to learn the Fourier series, what is the starting point? Which point? So if you have a sine wave, what is your starting point? You can say, I can start from here. Is it okay? Okay. Can I start from here? Okay or not okay? If you have a sine wave, it is continuous. Do you know where is the starting point? No, right? If you use a scope to measure this waveform, it is like this. Then I ask you, where is your starting point? It could be here, it could be here, it could be here, right? So any point, because it is periodical. No start, no end, right? Periodical. So every point could be start. So now we choose our starting point. So how can we choose our starting point? We say this is one period, 2 pi. And this is 1/3 of period. So it is 2 pi divided by 3. Okay. So we have the 10 ohm duty. We have the whole period of 2 pi. So what is our start? We pick up this one. This one. Is it okay? Okay, because any point could be start. Right? The starting point has no limitation. So if we choose this, we say this is my start. Then what is your period? From here to here. This is 2 pi, right? It is okay. So now I choose this is my start, and this is 2 pi. This is 2 pi divided by 3. Why do I choose this way? Because if I choose this way, I get some advantage. What is my advantage? It is symmetric. Symmetric, right? If I cut here, then this half equal to this half. It is symmetrical. If you choose symmetrical, then what can you get? You can get some advantage because your sine components always 0. So you get some advantage. So now we choose symmetrical. Then we can make sure the cylindrical waveform, cylindrical components should be 0. So we do not have the Fourier series of the sine components. We only have cosine, no sine, because it is symmetrical. How do you know we do not have sine? If you put this here, put this here, put this here, put this here, and then you put a sine wave. So a sine wave, maybe something like this, sine wave, and a sine wave like this. So this is plus, this is plus. So after you do multiplication, it becomes plus. This is minus, this is plus, this is minus. So after you multiply by sine, this is minus, this is plus. The average becomes positive. Right? So you can make sure the sine wave should be 0. We only have cosine. So the sine component should be 0. you can check the Fourier series. They always tell you if you have a waveform, the waveform is symmetrical, then your sine component should be 0. This is why we always use triangular to do the modulation. We do not have the source piece. If we use symmetrical, this is symmetrical, then the sine component is 0. If you use this as carrier, then sine component is not 0. So we have to choose symmetrical and make sure the sine component should be 0. So we only have cosine components. What is your cosine components? You call sine components is an. There is sine components. It is equal to 0. And now we calculate cosine components is Bn. So what is Bn? Do you remember what is Fourier series? It is minus 2t. How about this? This is 2t. How about this? This is 2t. And then this should be cosine n omega t multiplied by ft multiplied by d omega t. This is Fourier series, right? So you learn what is Fourier series. You learn the cosine component should be this way. So what is t? T is 2 pi. So it's minus pi, 2 pi. How about this one? This is 1 divided by pi. How about this one? This is cosine n omega t. This is ht and d omega t. So you can easily compute this mean. So you integrate from minus pi to pi. So this is pi. This is minus pi. So you integrate from minus pi to pi. So how about this one? We call the whole period is 2 pi. But this one is 2 pi divided by 3. We call it is 2 pi divided by a. A is 3. Can we say this way? A is 3, right? 2 pi divided by 3. So if we want to integrate from here to here, here to here, but here is 0. So we only have from 0 to pi divided by 3. So we can say it is pi. However, we do not, this is always 0. It is useless. We only have this one. So we can say this is pi divided by 3 and by 8. How about this one? Minus pi divided by 8. So we integrate from this point to this point. Right? And then we have cosine n omega t. We have ht. We have d omega t. Because the other time interval is always 0. So we don't need to calculate 0. Then we can get the result. So we use calculus to compute. Then we can obtain the result. So we can obtain this result. And then we can obtain the final result. So it is not too complicated, right? Step by step, you can compute the cosine component. It is like this. So how about an? An is always 0. How about a0? So now we want to calculate A0. A0 is average. Average. So we want to calculate average item. How can we calculate average? So one period is 2 pi. So from here to here, so minus pi a to pi a. The amplitude is 1. So 1 d omega t. So then we have 2 pi, and then we can get pi a minus pi a plus pi a. So we obtain the average is 1 divided by a. So if a is 3, and then if a is 100, then which means this becomes narrow, right? Then becomes small. If a is equal to 1, then it occupies whole 2 pi. Then the DC value becomes very large. So we can obtain this is correct. So how about the Fourier series? The Fourier series include 3 items: average, an, and bn. So we can say ht equal to average here, average, plus an sine, but it is 0, an sine, and bn. What is bn? Bn is 2 pi and sine n pi divided by a, sine n pi divided by a, we can say by a, and divided by n, and then cosine n omega t. So we calculate the value. We can copy the value. The value finally is here. Here, this is bn. So bn is 2 pi, and this is sine n pi a divided by n. Right? You copy this one to here. So this is bn cosine n omega t. An is 0. This is DC value. This is DC value. So we have 3 items. Okay. So what is the value? We can extend this value. First, we have DC value. This is DC. Then next we have n equal to 1. What is n equal to 1? So we have 2 pi sine n equal to 1, pi a n equal to 1 divided by 1. So divided by 1 means nothing. Then cosine n equal to 1 omega t. So what is this? This is force harmonics. So we call this force harmonics. The frequency is omega. And then we can calculate the second one. Second one is second harmonics. So we can obtain 2 pi 2 sine. This is 2 pi a n equal to 2 cosine 2 omega t. So this is second harmonics. Okay. So if you design a DC to DC buck converter, then you have the duty cycle like this. So you have input, you have switch, you have diode, you have inductor, you have capacitor, you have resistor. So you have a buck converter, right? You have the duty like this. So DC to DC, what do you need? Do you need harmonics or do you need average? average. So if you design a DC to DC, which item is the most important? This item or this item? So this is important, right? So you need a high DC or low DC? High DC. If you need a high DC, A should be small or larger? Small. If A is equal to 1, then what happens? You occupy 2 pi, which means always turn on. Then you can get very huge DC. If A becomes 100, then your duty is 1%. Your output becomes very small, right? So if you design DC to DC, what do you need? What do you want? You want the high DC. So if you design DC-DC converter, you need a high DC output. If you need a high DC output, A should be small. A should be equal to 1, right? Equal to 1. Then you have very high output DC, but a small harmonics. Then this is what you want, right? So if you design DC to DC, what is your purpose? You have high average and a low harmonics. So this is what you want. So the 60 Hz should be small. 120 Hz should be small. But the DC value should be very high. On the other hand, if you design inverter, do you like DC? If you drive a motor, do you like DC? No, right? So DC should be 0. So then DC should be 0. If DC is 0, then A is small or larger? Larger. A should be larger. If you design inverter, what you need is 60 Hz. So you hope this becomes larger. So maybe the fundamental frequency should be larger. How about the second harmonics, third harmonic? You should be reduced, right? Because you don't like harmonics, then the harmonics should be reduced. So then you can decide which kind of duty do you need. If you design DC to DC, you need DC voltage. If you design DC to AC, then you need fundamental, right? You don't like DC value. So we can decide the duty cycle. So we can see the switching function is very powerful because we do not have waveform, but we can learn what is the output voltage, what is the input current. So it is quite useful. So next step, we want to explain how can we use the matrix converter to develop the DC to DC converter. So how can we use the matrix converter to develop the DC to DC converter? So we have example. So if we want DC to DC, then the output are only 2 lines. The input are only 2 lines. So we discuss 2 by 2 matrix converter for DC to DC. Because DC only have 2 lines, one positive, one ground. So we only have 2 by 2. So then how can we draw this matrix converter? We have 2 lines. We have 2 lines. Okay. So we have 4 switch. 4 switch. So we call S11, S21, S12, S22. Then we have current sink here. We have voltage source here. So it is 2 by 2. 2 by 2. So we have I out, constant current. We have constant voltage. So how many switch do we need? 4 switch, right? 4 switch. So we call this is input. We call this is output. However, if this switch open, then the input ground and the output ground not connect. So if you have a buck converter, like this, then you say my input ground and the output ground are not connected. Do you think the circuit will work or not work? Never work. Because one circuit has only one ground, right? So your input ground should connect to the output ground. Then what happens? This is input ground. This is output ground. Then the switch should be open or closed. You have no reference, so it is not a circuit. A circuit should have common ground, right? So, do you think this switch should close or open? Close. So, if this switch is closed, always closed, do you like to spend one switch always closed? If you have a door, the door always closed, do you need this door? No need. It becomes a wall, right? So if this is always closed, then what happens? So if this is always closed, then this is always closed. So if in this line, this is this line. In this line, if I close this one, then what happens? Short circuit. So can I close this one? If I close this short circuit, do I like short circuit? No. So I never close this one. So this is open. If this is short circuit, this is open. Do I need one switch always open? One switch always short circuit? No. So for this switch, if the switch is always closed, do I need this switch? I use a wire to connect, then they always close, right? So in this case, what happens? We don't need this switch, and we think this is always tied together. So then we can remove 2 switches. We can save money, right? So we only have 2 switches. So from the topology, you use your own brain. Then you say 4 switches is not good. 2 switches is enough because it is redundant. So we can have some idea. S22 always 1. S12 always 0. So we can remove 2 switches because it is redundant. It is useless. So it is redundant. It is useless. Then what happens? We can change the topology to 2 switches. So we have 4 switches Right. Now we only need 2 switch. So we have S11, S21, we have I out. Here, we can go back to here. This one always tie together. This one always turn off. So we have VDC here. So if this is always turn off, then we can remove this one. This is always tied together, then we can have this circuit, right? To simplify the circuit, we can have this way. So this is IDC, this is IN. So this is IDC, this is IN. Then this is I out, and then this is V out. So how can we design this circuit? We can redraw this circuit. We have V in, VDC here, and we have I in here. Then we have switch S11 here, and then we have switch S21 here. Then we have ground here. Then we have current sink here. So this is the circuit, right? So totally equal. We can design this circuit. So if we design this circuit, then what happens? We have DC input. We have I in. We have S11. And then we have S21. And then we have switch. We have current sink. So this is I out here. So now we have to choose the switch. What kind of switch should we choose? For this switch, we could be turned on, we could be turned off, right? So can you choose a diode? Can you choose a diode to replace S11? Is it a good idea to choose a diode? Here, can we choose a MOSFET? Here, can we choose a MOSFET? We use 2 MOSFET. Is it okay? So what kind of device should we choose? So this is constant current, which means if this turn on, then short circuit, right? So if this turn on, this should be turned off. If this turn off, this should be turned on. So if we use 2 MOSFET, then we have to control the MOSFET, right? If this turn on, then short circuit. So you have to design a delay. If delay is too long, not good. If delay is too short, then overlap, short circuit. So do you like to scan the 2 MOSFET? Yes or no? If you think yes, please raise your hand. If you think no, please raise your hand. The answer is no. So how can we choose? Can we choose a track here? A track here. Then we can turn on, turn off. Yes. But it is too complicated because we need a high frequency. Track is not phase frequency, so it is not good. So what can we choose here?